Thanks for the introduction from Professor Martins. And I'm Ray, and I'm from the University of Michigan. And today I will present our work, WebRobot, which is an interactive system for web automation using programming by demonstration. Imagine you're a data scientist and you want to script the ratings of each movie from the IMDb website. Or you want to script the location and phone number from the subway stores. You'll probably want to write some script for them because you want to automate this task. However, writing scripts like this is not very easy and it's challenging. Researchers have studied on the challenges faced by the programmers on writing these automation scripts. And the first challenge is that for this script, you also want to write some for loops and while loops. And these loops are sometimes nested. So the structure of this script is quite complex. Also, you may want to use some generalizable selectors for each element for the website. On the website, for each element, you will have thousands of alternative selectors. And find one that is stable and can be used in the for loop is very hard, because it's only a few of them can be used. So the user will probably ask, can someone write the scripts for me? And our idea is to use interactive programming by demonstration to tackle this problem. And here comes WebRobot. In WebRobot, the user wants to provide some demonstrations to the synthesizer, which is a trace of actions. After providing the demonstration, the synthesizer can synthesize programs. And our system can use the synthesis program to automate the task for the user. In particular, this synthesis process is interactive and continuous. For example, if the user wants to automate a task using WebRobot, the user first provides some demonstration to the synthesizer. The synthesizer will generate programs, and by executing these programs, the synthesizer can provide some predictions to the user and visualize it on the web page by highlighting. And the user can inspect these and choose to accept or not. If the intended prediction is not intended, then the user can continuously provide some demonstrations, or the user can also provide some demonstrations to review new patterns. So this whole procedure is interactive and continuous until our synthesizer can generate some programs which can automate this task. The difference between our system and previous system is that in the previous system, if the program generated is not intended, then the user will need to manually edit them. And this demonstrate and edit procedure will be divided into two phases. However, in our system, this demonstrate and inspect loop is continuous, which means that the user can continuously interact with the synthesizer until the task be automated. So let me show you an example of the real-world task, and I will use this example in the rest of this presentation. So this is a website where you can extract the location and phone number from the subway stores. And the task is to extract each store's address and phone number. There are 10 stores on each page and 5 pages in total, which means that you probably will not want to do it by hand. If using WebRobot, the user will first provide some demonstration. Here, he will first extract 2 stores from the website, and we will record that as an action trace. Each action in the action trace contains 2 components, which is action type and selector, which means how you identify each element on the web page. And here we use XPath to represent that. And our synthesis problem is that given action trace A provided by user, we want to synthesize a program P, and such program P should satisfy some requirements. First, it should reproduce A, which means it should be consistent with what the user did. And also, it should generalize A, which means it should produce more actions so that we can know what the user might do and provide some predictions. More specifically, by reproduce A, I mean that if we execute the program P and generate a new action trace A prime, the original trace A should be a prefix of the generated action trace A prime. So that means it's consistent with what the user did. And by generalize A, I mean that the generated action trace A prime should be longer than the original one, which means we can make some predictions, and that's why we can automate the task. So let's dig into the synthesis part and see what kind of techniques we can use to solve this problem. Traditional search-based synthesis will search the programs in grammar, and it is widely used for programming by example. However, our grammar is too large because we have a lot of action types and we have a lot of for loops, and we also want to generate some complex structures. So using the search-based synthesis will take us a lot of time, and we cannot do it in real time. What's special in our domain is that we have an action trace A provided by user. And actually, we can do better. We can leverage this to guide our synthesis. Therefore, this inspires us to use rewrite-based synthesis. There are already some existing rewrite-based synthesis, for example, egg, which is a state-of-the-art rewrite library using egraph from POPL 2021. And their key idea, in short, is to use a set of sound rewrite rules and perform the rewrite iteratively. For example, we have some rewrite rules here. The first is the associative law. The second is x divided by x equal to 1. And the third is x times 1 equal to x. These are rules that is correct by construction. And the general idea of existing rewrite technique is that given an expression, we iteratively match it to the left-hand side and rewrite it to the right-hand side. And if we do it until there's no new rewrite generated, we can find our intended program in the search space. However, for our domain, the input is a long action trace, and it is very hard for us to write some rewrite rules like the previous example. Even though we want to apply the existing techniques to solve our problem, there is possible some ways. For example, we can split the action trace into several parts and set the rewrite boundaries. And after set boundaries, we can use some E-class analysis and dynamic rewrite to deal with each part and rewrite it to a program. And if we do it iteratively, we can also generate a program. However, this existing technique is not practical in the real world, because the first, even if we know which to rewrite, it is still very hard for us to write some sound rewrite rules, because you need to do some matching globally, and you need to ensure many properties of it. Also, rule matching is very slow for a complex trace. In our task, the trace is like 20 to 30 actions, and we can extend this trace to 5 or 1,000. So the rule matching for such a long trace is very time-consuming. So the traditional rewrite-based synthesis does not work well in our domain. So what we can do? The fundamental challenge brought by the previous rewrite system is the sound rewrite rules, which means we need to check a lot of properties. And our idea is that we separated this into two phases, rewrite rules and sound afterwards. By rewrite rule here, I mean that we will use unsound rewrite rules as the first place and guess the rewrite locally, which means you don't need to check many properties, but just to make guesses. And then we will ensure the rewrite is valid by another procedure, which is called validation. So this is our idea, speculation and validation instead of the rewrite, sound rewrite rules. So our idea here is to replace the sound rewrite rules into a guess and check procedure. And it will be much faster, and the rewrite rules is easier to write, as I will explain later. So let's first see how we can guess a program structure. For example, in gray, this is the action trace provided by user. And we can actually guess this program structure using only a few actions from this trace. For example, we can guess program structure by these two orange actions. As you can see, it's very easy to observe that these two actions only differs in the green, which is the index 1 and 2. And we can take a guess. We can guess these two actions maps to two iterations of the same action in a loop body, which means we are looping them. And we can actually guess the for loop structure and the part of the loop body. We can also guess the looping variables because we see 1 and 2, and we can guess the next is 3, right? So after further examining the trace, we can complete this sketch, and we have our rewrite candidates. So the advantage of the speculation, as you can see, is that the rewrite rules is very easy to write. We only need to write some comparison and similarity detection. And the rewrite rules is very easy to match because we match it locally instead of globally. However, as I mentioned before, our speculation is unsound, which means we need to do some other steps. There are two questions. Is this guess correct? And which part it can rewrite? So we need another process, which is called validate. In validation, our key idea is to validate candidate rewrites using trace semantics we designed. Recall that we have a list of action A, and after speculation, we get a bunch of rewrite candidates, right? And we want to know if that's correct. So we feed them into an evaluation engine and designed by our trace semantics, and we can evaluate this program and generate a new action trace A prime. By comparing A prime and A, we can actually see if this rewrite is valid and which can it rewrite. For example, this is the previous candidate, and after evaluation, we got A prime. And by checking A prime against the original trace A, we can see, oh, there's a match. And then we can safely rewrite this part to a more general program, which is our right candidate, because we have validated it. So even though our guess is unsound at the first place, our rewrite rule is sound after validation. So we can change the rewrite using sound rewrite rules to these two speculation and validation procedure. If we apply it iteratively, and we can each time rewrite a part of the program to a more general one. And in the end, we will have a program with doubly nested for loop, and it can automate the task for the user. For the evaluation, we evaluated WebRobot on 66 tasks from iMacro's forum, which is the online forum for web automation tasks. And we selected tasks with complete description, and we manually wrote Python scripts. For these tasks, there are many required features like data scraping, data entry, navigation, and pagination. And some of these tasks requires 2 of these features or 3 of these features, so there's an overlap. And our result shows that the WebRobot can successfully generate the intended program for 69 of 76 tasks, and the synthesis time is within 1 second. And also, the user can get the intended program within 10 manually demonstrated actions. As for the program structure, we are able to generate doubly nested for loop for 32 of these tasks, and larger than 3 nesting level for loops for 6 of these tasks, which means that WebRobot can deal with complex structures very easily and faster. We also invited some users to try our WebRobot systems to see the usability. We invited 8 participants to perform 5 tasks using WebRobot. And the result is that all the participants can solve each problem within 90 seconds and 10 manually demonstrated actions. And we also get feedbacks like quite decent and smooth. In order to see if our speculation and validation technique is indeed faster than the previous work, we also built a baseline for 6 benchmarks because it takes a long time for us to write rules, so we didn't apply to all the benchmarks. And the baseline built with egg will take 200 seconds to generate doubly nested for loop and cannot generate 3-level nested for loop within 5 minutes timeout, while WebRobot can solve all the problems within 1 second, which means that we are indeed faster than the sound rewrite rules. So that's all my presentation today, and I'm happy to take any questions. Thank you.
Thank you for the great talk. Anyone has a question in the audience? If so, please come a bit further. Sorry. Give you the mic. Can you come here? Sorry. Yeah.
Yeah, thanks for the great talk. I have a question about synthesizing. If you have a scraping task where kind of what you want to scrape maybe depends on the data itself. So for example, I only want the addresses of subway stores that are open. I was wondering if you have any way of synthesizing like conditionals, and if you have any thoughts on how you do that, or if you have done that.
Actually, we do not support any conditional because we don't have a way for the user to demonstrate that condition. But using our technique, we can definitely add it by adding some if or something like that. Actually, we have some follow-up working on this. Yeah.
Okay, cool. Thank you so much.
Thank you.
Hi, great talk. I was curious if you tried to do something like inverse transformations, since you had that example with egg. So, there's been work where people have tried to use equality saturation for this kind of synthesis, but some of the rules are actually unsound, but it's fine because you can add some annotation to the expressions that these rules generate, and then you can later on get rid of those annotations. Like, would something like that work? Or I'm curious if you.
Actually, we have tried to implement this using egg, and actually we have wrote some rules in the egg for using the E-class analysis and something like that. But one thing we observe is that first, if you want to rewrite programs, you first need to split them. And such splitting will take a significant amount of time if the trace is very long. And also, because our program's length is not fixed, so because sometimes there are 3 actions inside or 2 actions inside to write a for loop. So this variadic program length will cause some problem for the concrete rewrite rules or sound rewrite rules. Yes, so we actually tried that, but it's very slow. So that's why we are proposing this speculation and validation methodology.
Got it. Thanks.
Yep.
Hi.
Hi.
So the interaction model that you showed seems similar to work by Sarah Kaysen's, say, like the Russelin work. I'm wondering if you can say any words sort of comparing, if you did any comparisons against them.
Yeah, in Sarah Kaysen's work, which is Helena, what we automate a task is to demonstrate the first row that the user wants to extract, right? But after that demonstration, what we can do is to manually edit the program. So this is divided into 2 phases. But in our work, we do not have such clear separation of phases. The user can continuously provide demonstration in a interactive way. And so I think the difference is that they have explicitly 2 phases, but we can continuously let the user interact.
Okay, thanks.
Yeah.
So I guess I also have interesting question. So I noticed that synthesis times were very fast, right? So
yes.
Is it because of the separation that you did with speculation and verification? Was that the key ingredient to make it so fast?
The synthesis is very fast is because we only perform rewrite by observing the local patterns. We do not consider the whole trace. So it is very fast for us to generate rewrite candidates. And also, if you can see our validation procedure, it's a linear process. So adding these 2 together, we can generate rewrites very fast and validate very fast. So that's why we are much faster, because we do not need global information of that.
And that's a nice property, especially since you're interactive, right? You want something very fast to be able to interact with the user and get information back. So you mentioned that when you're doing like the rewrite rules, that it was kind of hard to write them, right?
Yes.
So at the end, how many rewrite rules do you actually have? Is it hard to write new ones?
You mean the rewrite rules using egg or using our
I guess not the sound ones, right? I guess the sound ones were really hard, right? Yours are much easier to write. Can you give me some insight about that?
We actually have a total of 3 rewrite rules, on-sound rewrite rules. It's basically 3 rules where you guess different program structures. So it's totally 3.
Oh, awesome. Okay.
Yeah.
Well, thank you very much. Let's thank again the speaker.
Thank you.